I bet you've seen these typical videos of pieces dipped in liquid nitrogen that suddenly start to float as if by magic. No, they're not special effects. They're superconductors. Substances where electricity flows without any resistance, creating magnetic fields strong enough to do truly spectacular stuff. But they're not the only members of the Super Club. Say hello to Superfluid, a liquid so ethereal it can pass through barriers no gas could penetrate. It has zero viscosity, so nothing can stop it. And that's why it can generate currents capable of overcoming barriers all by itself. Superconductors and superfluids are a fifth state of matter, a quantum state beyond electrifying plasma. Helium, for example, only becomes a superfluid when it reaches a certain temperature, like water when it turns to ice. But why are superconductors and superfluids in the same category? They're very different. Shouldn't they have separate categories? Well, if you stop to think about it, there are similarities. In both cases, something flows unopposed and only appears at very low temperatures. What do the supers have in common? Today we're going to talk about Bose-Einstein condensates. But let's start with bosons. Think of this. Imagine you have a piggy bank full of money and a minor quandary: where to keep it. If you keep it at home, the money would be handier, but if you keep it at your parents' house, you'll be less likely to spend it. You can't decide, so you turn to the quantum world. You buy 2 boxes, put the piggy bank inside them in quantum superposition, and take 1 box to each house. Now the piggy bank is delocalized. It seems to be in both houses at once. If you need your money, you just have to open the box, and you'll have a 50% chance of finding it there, a risk you're willing to take. Meanwhile, your brother is watching the whole thing, and he's totally flipping over your dope plan. He has a piggy bank just like yours and asks you to put it in the boxes too. You agree, and together you try to superimpose the new piggy bank at the same time. But shocker, you can't get it in. A strange force won't allow the 2 piggy banks to be together in the boxes. What's going on? The answer is that the piggy banks, like electrons, protons, and neutrons, are fermions. Fermions are particles that cannot share the same place as another fermion, which seems logical, or even share the superposition, the same state. They can overlap, but they can't have exactly the same state. This is basically what allows us to exist. As electrons inside an atom can't all be bunched together near the nucleus, they each have to be superimposed in orbitals of increasing energy, almost as if they were piling up on top of each other. This fermionic property is what gives an atom structure, the variety that lets them form all the chemical species we know. In contrast to this, we have bosons. Bosons don't need to pile up. They can be in the same superposition as their buddies. A legendary example of a boson is light. You can overlap as many beams of light as you want in the same place, and they'll just join forces. The most radical example of this is the laser beam. The photons that make up light are bosons. This is the dynamic that Bose discovered, and Einstein revisited it to ask this question: what if you could have a gas made not of conventional molecules, but of bosons? In this article written nearly 100 years ago, he predicted that something would happen to this gas if the external temperature were low enough and the bosons didn't have enough energy to keep bouncing around. They would seek the maximum state of rest. Just like skaters without momentum all end up at the bottom of the ramp. Only here, the bosons converge in the same state, the same superposition, and with nothing to prevent them, they all crowd together. It's as if there was just one chair at a party, and when people got tired, they all sat in it and melded together. Einstein believed that this part of the gas would condense, just as the steam from a boiling pot condenses in droplets on the lid. This new state of matter is the Bose-Einstein condensate. But if Einstein had known what really goes on in here, I think he would have been horrified. Because in this process, the particles quantumly entangle, forming a quantum condensate. The basic idea is that the condensate's components lose their independence and become one. They're all coordinated, and that coordination is precisely what allows superfluidity and superconductivity to appear. Because think about it, what do the electrical resistance and viscosity of a substance have in common? They're both products of friction. In the case of a fluid, viscosity is caused by collisions of its stray molecules, the ones that don't go with the flow. And the same happens in an electrical current. Resistance is the result of maverick electrons. They're consequences of disorganization. But in a quantum condensate, all particles are organized. You could say that entanglement coordinates them. And since none of them step out of line, no randomly flowing electrons, no offbeat helium atoms, perfect conductivity and fluidity appear. This is the origin of the supers, which are basically somewhat more complex Bose-Einstein condensates.
Hold on! You just said that electrons, protons, and neutrons are fermions, not bosons. So how can groups of helium atoms or electrons form a condensate?
The key is that the whole is greater than the sum of its parts. I won't go into too much detail, but what happens is that when a lot of fermions get together, they can form a system, a quasi-particle, that doesn't behave like a fermion. In the case of helium-4, it's easy. 2 electrons, 2 protons, and 2 neutrons together act like a boson. That's why when helium-4 is cooled, it forms a superfluid. The case of superconductors is more bizarre. What happens here is that electrons below a certain temperature form pairs, Cooper pairs, that act like bosons and can condense. But why do they pair up? What makes them do that? These are mysteries now being studied at the IFIMAC. For example, by using ultra-high magnetic fields, Cooper pairs can be broken down to study the glue that holds them together, which scientists hope will give them clues on how Cooper pairs are formed. We're already starting to use this fifth state of matter in everything from quantum computing to cables with practically zero loss. As someone once said, "We just discovered ice. Give us time and we'll invent ice cream." That's all, folks. If you want more science, just hit the subscribe button. And thanks for watching.